they are developed very well also. Now that's the last part, outcoupling efficiency. At the first stage of OLED development, people just apply the ray optics. And then if you just, this is the OLED structure, this is a metal electrode, ITO, and OLED, organic light semiconductor layers. And you can say this has a refractive index of 0.7, for instance, but the area is 1.0. So the light emitted in this layer experience some total, some reflection at the interfaces between this ITO and also the glass and the air glass substrate and so on. So that if we just simply calculate this outcoupling efficiencies using ray optics, it turns out to be this equation. And if you just put this n 1.7, this is about 20%. So 20% times 25% for fluorescent OLED, that's the allowed radiative transition, that is the maximum is 5% for fluorescent, and phosphorescent 20%. That is the case. So people just had believed the maximum EQE limit is 20% up to 10 years ago, many cases. And many papers describe the maximum EQE of OLED achievable in OLED is 20%. But it turns out that that model is too simple to describe the characteristics adequately. Instead, classical dipole model turns out to be more adequate to describe that on cases. In such a case, in the model, the extone is treated as oscillating electrical dipole, and then that is embedded in this microcavity structure, and adopted in this dielectric, embedded in these dielectric layers inside of the microcavity OLED structure. And then the radiation power can be obtained as a function of many parameters in the device, location of dipoles and orientation of dipoles, and radiative quantum yield. And you need to consider Purcell effect, which has the radiative dipole transition rate influenced by this electric field from these cases. So if you just consider the material properties of emitters, you can easily take this dipole orientation of these emitters and PLQI, and the optical constant, or the other ones are the device parameters. So this where I just selected these material properties and calculated for the optimized device structure to get the maximum achievable OLED structures. Now I just put the dipole orientation as these characteristics of that. That's because the radiation pattern from the dipoles is like donuts and propagation like this. So for vertical dipoles, light is emitted along this horizontal direction along this layered molecules. So most of the light is confined inside of OLED without outcoupling. But for horizontal cases, it's a vertical emitted 50% of that to the vertical directions, to these directions, so that the outcoupling efficiency is much larger. So we need to consider this effect of orientation and also PLQI, that's virtual parameters. And this is the result, and we got these diagrams, this PLQI and horizontal dipole ratios. It turns out that the outcoupling efficiency with 100% dipole orientation, horizontal orientation, and 100 QLQI is about 45%. This was for the if devices are optimized and the electrical loss is 0 and so on. So this after that, now these people just believe that with the proper design of OLED devices, maximum EQE can be 46%. And we needed to check whether this calculation is correct or not. So we proved this one during the last about 10 years. And then we just synthesized in collaboration with one professor in the Univ. And then you can find that the horizontal dipole ratio can be changed to increased to 86% with high PLQI to get the calculated EQ of 38%. Now we actually tested a whole bunch of iridium complexes and to find that our calculation scheme is quite good, so that the theoretical prediction seems to be quite good. Also, the device we use the X-plex host, and that gives a very good charge balance, extern formation efficiency of 100%. And then we could get the almost perfectly horizontally oriented dipoles using crystal OLED using this platinum complex, and the PLQI was also very high to realize the 39% of EQEs, I'm sorry. And then this is the improvement of devices during the last 30 years, and to get this 40% or approaching 40% EQEs. But a little bit recently a little bit higher, but almost the same as 40% are reported in these devices. Now let us consider efficiency roll-off. We use the same dopant, OP-ECEC, which has 76% of horizontal dipole ratio, 95% of PLQI. And it turns out that theoretical limit of outcoupling efficiency is about 30%. However, when we fabricate device using different device structures, we obtain a different EQE here. And first of all, this device shows less EQE, and this mixed host shows a little higher efficiency, but still below 30%, and this gives this kind of tendencies. And with the increasing current density, this device shows the efficiency roll-off. So this has this advantage to utilize to get the high brightness from that. So many propose that this one, the origin of this one, electrical loss, includes the origin of this roll-off is proposed to be coming from the electrical loss and the extern quenching. So bimolecular quenching, extern polaron, or the quenching interactions. And then we've developed the quantitative analysis method. To analyze that, we got this one. This behavior, this one is low because of the poor design of that, but we compromised that to get the charge balance equations. Electrical loss is small, but optically poorly designed. So loss of 7% in this device, even at the low current densities. Also, we quantitatively could get this electrical loss factor and the external quenching by molecular quenchings. Here in this device, you see that the electrical balance is the main player to get the roll-off efficiency roll-off. That can be extended because the electron injection barrier is so small here to that. But this case is gives a smallest efficiency roll-off and well-designed, the high efficiency, because well-designed and barrier is quite high, and so on. Therefore, X-plex host, this is X-plex host, has been widely used in practical devices. Now, finally, I will discuss on the degradation of OLED. Degradation is an important issue in OLED, especially in blue phosphorescence and the TADF OLED, because of the short lifetimes, fluorescent OLED is used and power consumption is big, and also image burning, image sticking is rarely, actually sometimes actually observed in OLED devices. The degradation process has been studied from the beginning of the OLED research. At the first stage, people just actually get rid of this extrinsic degradation part, which is induced by air, light, and delamination, and so on. Nowadays, technology is well developed so that and also materials are developed, well developed so that the extrinsic degradation is almost negligible. Now this intrinsic degradation, especially in blue, is the problem. Actually, the origin of intrinsic degradation origins have been proposed by actually as the extron polaron, and the extron itself, and the radical ion pair between host and extron, between host extron and the dopants, and so on. Still, we recently developed a model to get the quantitative analysis of that. This is the blue device. This is the in collaboration with the Samsung Display and Samsung site, Advanced Institute of Technology, and this is blue device, and the EQ is quite high, 18%, and good color purity, and the lifetime is not excellent but quite good, and also driving voltage is high. So this is the degradation, usually observed degradation. Originally, at constant driving, originally 100%, but it is reduced with time to gradually. Here in this case, after 20 hours operation, actually the light emission was reduced by 50%. At the same time, driving voltage increases with that. So we need to quantitatively analyze that. Many papers have been reported, and so that we also performed one way and developed a model. I don't know, go into details of that. And if you are interested in, probably you can actually look at this paper. And then if I just say the result, you can see our best fit gives excellent, our model gives excellent fit with experimental data. And then it turns out that the degradation is coming from the polaron for this specific device. And also this, we can quantitatively actually get the portions different from the degradation quenches formed by different mechanisms, extron itself, polaron or environmental cases by these cases. Also, we could get the EQ variations, and our model describes excellent. These are the experimental data. These are our model. Also, that actually can be applied to different initial intensities. So we are very much interested in this developing model, so that we can, I think, now quantify the origins and where the quenches are formed in the EML or the charge transporting layers or just the environmental effect, which is incorporated during the fabrication processes, even in the high vacuum cases. All right, so this is the discussion of EQE and also the degradation processes. Blue, the red and green OLEDs actually are very good nowadays in terms of color purity, lifetime, and also the efficiencies. However, the blue case is different, and still, as I mentioned, fluorescent device is used, so efficiency is low, and so on. But the recent development is quite promising. So I'll show you one paper from Samsung Display. They use this mixed host with this blue emitting dyes to get the about 23 or 5%, 25%, over 25% EQs, and then very good color. CI coordinate is below 0.2, and then this is the long lifetime at 1,000 nits, if I am correct. So this you see this 50% degradation to 70% of the iron, so-called LT70 is over 1,000 hours. So I think the development or commercialization of blue phosphorescent or TADF OLED is quite promising in near future. So with the development of efficiency, lifetime, and the materials, you see the OLED are used in the small display and the TV and the CNG, and I think that OLED is becomes dominant over LCD nowadays, and so on. In conclusion, in summary, this lecture introduced electronic structure, electrical and optical properties of organic semiconductors, followed by device physics of OLED such as efficiency roll-off, and degradations. Thank you for your kind attention.